Pluto is a far-off and bewildering minor planet, once an individual member of our planetary family. However, recent disturbing declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with an astounding revelation. They proposed that this chilled world is on a collision course with Neptune. But how could this occur, and what may be the consequences of such a critical event? Are we seeing a charming, grandiose, capricious event, or is there something else to this oncoming, boundless impact? Join us as we research the possible results of a Pluto-Neptune impact. Pluto, a former planet that was scaled back to a dwarf planet, is noteworthy because of its odd orbit, and it remains a subject of interest and study in the astronomical community. As shown by recent assumptions by leading experts, Pluto's orbit is perilously close to Neptune's. Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a possible dangerous collision between these two planets, which would pose a significant risk to Earth. How is such an event even conceivable? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It requires a complex 248 years to complete a single orbit, which means that since its discovery in 1930, it hasn't even finished one full revolution yet. However, the interest doesn't stop there. Pluto's orbit is marked by its extraordinary bent shape, deviating significantly from the almost round orbits of the major planets. What makes Pluto's orbit even more surprising is its inclination of 17 degrees to the ecliptic plane. The course Pluto follows is significantly steeper compared to other planets. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's. For at least 20 years in each orbit, Pluto actually moves closer to the Sun than Neptune, defying what we'd expect from their positions in the planetary system. This prompts the natural question: why hasn't Pluto slammed into Neptune? The answer lies in the gravitational impacts of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers attempted to determine its unique orbit. Unlike other planets, whose orbits lie close to the ecliptic plane, Pluto's orbit stood out with its deep inclination and bent shape. The mystery deepened with the realization that Pluto's orbit does indeed cross Neptune's. The stability of Pluto's orbit, despite these complexities, is proof of the intricacies of celestial mechanics. The three-body problem in space is about figuring out how three bodies, like Pluto, Neptune, and the Sun, move and affect each other through their gravity. Pluto's orbit is, in fact, chaotic. Minor deviations in initial conditions can lead to significant differences over long periods. However, these surprising properties of Pluto's orbit have been found to maintain stability over particularly long timescales, keeping tumult in check. Recent simulations have helped us understand how the giant planets, like Neptune, Jupiter, and Saturn, influence Pluto's orbit around the Sun. Jupiter's immense gravity is strong enough to keep Pluto on a stable path for potentially billions of years. These factors are crucial in maintaining order and consistency in celestial mechanics. Without these factors, our solar system would be a place of far greater chaos and unpredictability. Pluto's orbit is a striking representation of celestial mechanics at play, showing both stability and turmoil within our planetary system. The unique characteristics of its orbit, affected by the gravitational forces of nearby planets, particularly Neptune, highlight the complex and dynamic nature of space. Predicting significant events, especially when they involve chaotic orbits like Pluto's, presents tremendous challenges. The inherent unpredictability of these systems means that long-term forecasts are often filled with uncertainty. While mathematical simulations offer a solid means for understanding and predicting the future behavior of celestial bodies, they also highlight the limits of our predictive capabilities. So, why are prominent astrophysicists only now raising concerns about a potential collision between Pluto and Neptune? Despite the various complex forces working to prevent such an event, Neil deGrasse Tyson and Michio Kaku, both renowned figures in cosmology, have expressed concern about a possible impact between Pluto and Neptune. If Pluto and Neptune were to collide, it would be a captivating and catastrophic event in our solar system. The impact would release an enormous amount of energy, likely destroying Pluto due to its smaller size and icy composition. Debris from the impact could scatter across the solar system, possibly presenting a risk to other planets and their moons. For Neptune, such an impact could alter its current atmosphere and potentially its orbit, depending on the specifics of the crash. Michio Kaku, a prominent theoretical physicist known for his work in string theory, brings a unique perspective to the conversation. His views on the future of space exploration and the connection between celestial mechanics and theoretical physics offer valuable insights into the mysteries of major phenomena like Pluto's orbit. Understanding the complex gravitational interactions and orbital mechanics of celestial bodies like Pluto can yield significant knowledge for future space missions. This information can help in navigating the solar system more effectively, predicting potential dangers, and even planning missions to the outer reaches of our solar system and beyond. The lessons learned from studying Pluto's orbit can be applied to exploring other celestial bodies, providing a roadmap for how we might approach and understand distant worlds. In terms of planetary science, celestial mechanics and theoretical physics are deeply interconnected. The movements and interactions of planets, including the gravitational dance between Pluto and Neptune, relate to the fundamental principles of physics. If Pluto and Neptune were to collide, it would be a monumental event in astronomy, offering a unique observational opportunity that might even connect to string theory. String theory, a theoretical framework where the point-like particles of particle physics are replaced by one-dimensional strings, aims to explain the fundamental forces and matter in the universe. The impact could create extreme conditions of energy and gravity, potentially leading to circumstances where predictions made by string theory could become observable. For instance, the high-energy impact could offer insights into the behavior of fundamental particles and forces under extreme conditions, a key area of interest in string theory. While the direct impact on Earth would be minimal due to our distance from the outer solar system, the scientific implications of such an event could be significant, potentially contributing to our understanding of the fundamental nature of the universe.